Hello, I'm Laur Fisher of the MIT Environmental Solutions Initiative, and this is Today I Learned Climate. Last week, we talked with Professor Desiree Plata of MIT to learn about greenhouse gases like carbon dioxide and methane and how they interact with the atmosphere. And in our conversation, she said something fascinating.
One of the unique ways that we could start to change the rate of global warming in our lifetime is actually to target what are called short-lived climate pollutants.
Like methane. It only lasts around 12 years in the atmosphere, but in that time, it traps much more heat than CO2. So today, Professor Plata is back to tell us, how do we tackle methane? Oh, and she is bringing a special guest with her.
So I welcomed a baby to my family just a few short months ago. So she's joining us for our call today.
You'll hear baby Plata chime in once or twice in this episode. Okay? Okay, let's jump in.
So in the room that we're sitting in, for every million molecules in the air in front of us, 420 of them are CO2, and only 2 of them are methane.
Wait, just 2 of every million molecules?
Yeah, that's right. And the accurate number is 1.91 parts per million methane in the atmosphere.
1.91 parts per million is actually a relatively big number for methane.
In the last 150 years or so, we've seen unprecedented rates of increase in methane. If you look at pre-industrial methane levels, by looking at gas bubbles that are trapped in ice, they were around 0.76 parts per million in the atmosphere. So it's more than doubled, actually, since pre-industrial times.
Compare that with CO2, which is up about 50% from its levels in the 1700s. And the thing is, CO2 can last hundreds of years. So we've had a lot of time to raise its levels that much. Like when people shoveled coal into the furnaces in the Titanic, that coal released CO2 that's still in the atmosphere today. But remember, methane only lasts about 12 years in the atmosphere. So most of the methane up there, whether it's natural or man-made, was emitted just since the creation of Instagram. So where's it all coming from?
Methane kind of comes from everywhere, actually. Anywhere where you've got the accumulation of organic matter and you're kind of running out of oxygen, you can start to generate methane.
You know how we breathe in oxygen and breathe out CO2? Well, there are certain microorganisms, scientists call them methanogens, that live in places with very little oxygen. So they evolved to take in CO2 and put out methane. They live in places like wetlands and in the bottoms of lakes.
Methane also forms in the guts of what are called enteric fermenting animals. So these are animals like cows and sheep, and part of their digestion process actually leads to the generation of methane through the microorganisms or bacteria that live inside their stomachs.
There's also methane deep underground.
You can imagine a long time ago, animals or plants dying, getting buried deep below the Earth's surface. So you kind of cook and crack and crush all of the organic compounds, and they react to form things like fossil fuels. So coal, oil, and natural gas. If you're sitting in the United States right now and listening to this podcast, the chances that your home is heated by natural gas are pretty good. And at least 98% of the natural gas coming out of your pipeline is methane.
And that's why some folks refer to natural gas as methane gas. Now, when you burn that gas for heat or electricity, the methane reacts with oxygen and produces CO2. But if it escapes before we burn it, say from a leaky gas pipeline, that methane does go right into the atmosphere. And since methane gas is often found along with other fossil fuels, it's common for some methane to be released during coal mining and oil extraction and processing.
So typically, methane emissions are categorized as anthropogenic and natural. And the anthropogenic means that it's human-derived, and natural is kind of this implication that it's from wetlands or lakes or those types of sources. But the reality is that humans are changing the Earth system so much, even the natural sources have been augmented.
Humans create a lot of low oxygen environments that methanogens love, Like there are over 400 million acres of rice fields around the world, and many of those are flooded, creating, in effect, little lakes where methanogens thrive. And to deal with our garbage, we've built thousands of landfills to lock our waste under mountains of soil. Again, ideal conditions for the microbes that make methane. And while it's natural for cows to burp methane, it's humans that are raising 1.5 billion of them around the world. Clearing and draining wetlands can also release a lot of their methane all at once. And even more methane is locked in frozen soil in the Arctic, which is starting to thaw as the world gets warmer.
There's major concern that if we don't start to control the rate of climate change in the next couple of decades, that those types of processes could be accelerated. In other words, our bad behavior is going to come back to bite us, to make things even worse, even faster.
While methane comes from a lot of different places, there are some especially big targets to start reducing emissions.
People want to target what we call the low-hanging fruit. So methane emissions from the natural gas distribution system and extraction system. So things that are in a pipe and might feasibly be easy to stop because of that. Some of the other proposals include things like lowering water levels in rice paddies to reduce the formation of methane, having a better capture rate for methane that's coming from landfills, and feeding food additives to cows to get their gut microorganisms to produce less methane to start with.
Okay, any one of those could be its own episode, with its own benefits and challenges. But the one thing they have in common is that we could use some better data to help us identify the biggest methane hotspots.
Methane just hasn't had the historic attention of the scientific community that it really needs to get accurate assessments. I mean, it takes an army to measure methane emissions accurately.
Yeah, we know how much methane is in the atmosphere. It's actually not hard to know this. Since it mixes freely in the atmosphere with the other molecules, scientists can take air samples from around the world and pretty easily measure the concentration of methane. But to find a single source of methane emissions, say a gas pipeline leak, well, that takes a totally different kind of effort.
It's scientists who are going out to lakes, measuring bubbles coming up from the bottoms of lakes, being out in wetlands, measuring both in the wetland and above the wetland to see how methane is being emitted. It's going to dairy barns with handheld sensors. There's been a huge push over the last decade, I would say, to get satellites into the sky so we can start to look from outer space down to see how much methane is there and where that methane might be coming from. And those satellites provide an integrated picture of what's happening over large geographic regions.
And the world is taking methane emissions more seriously. 2021 saw the creation of an international agreement called the Global Methane Pledge, which around 150 countries have signed on to so far.
And the goals of the Global Methane Pledge are to cut methane emissions by 30 to 45% by 2030. If we could cut methane emissions by 45% by 2030, we would save 0.5 degree of global warming by 2100. It's a really big deal to be able to do that.
Many of these countries are following through on this pledge with concrete plans. In the US, for instance, it recently became law as part of the 2022 Inflation Reduction Act that large natural gas facilities and other facilities will have to pay a fee for every ton of methane that they leak into the air. And if those companies capture the methane before it enters the atmosphere, there's actually something very practical that they could do with it. They could burn it and turn it into CO2. That's what happens with the methane gas that we burn for heat.
So burning it or converting it into CO2 in some way is a brilliant solution and a pretty tractable technology if you have highly concentrated methane like you do at landfills and like you do in the oil and gas industry.
Some landfills have even started selling energy this way. Burning the methane that they produce is pretty much the same as burning natural gas in a power plant. Now, you might be thinking, wait, what? CO2 is a greenhouse gas. Aren't we supposed to be keeping greenhouse gases out of the atmosphere? Well, yeah, it's true. But if your choice is between a molecule of CO2 and a molecule of methane, Professor Plata argues that you'd much rather have the CO2.
You can take half of the atmosphere's methane and convert it to CO2, and the CO2 levels go from 420 parts per million to 421 parts per million. It's a minuscule contribution to CO2 in the atmosphere, but you would save close to 15% of the heating that we'll experience in the next 100 years, if you can pull that off. Dealing with methane emissions is an enormous challenge. It's hard to find methane. It's hard to fix leaks. It's hard to abate methane from dilute sources like wetlands and dairy cows and things of that nature. But that doesn't mean it's not worthwhile. Methane is uniquely positioned to change the rate of climate forcing in our lifetimes. It's the only greenhouse gas that you can abate and see a near-term effect before this baby graduates from college.
That's the end of our episode today. If you want to dig deeper into where methane comes from and what we can do about it, we have more information in our show notes. Or you can bring these questions into your classroom with our educator guide for this episode. Find them both at tilclimate.org. TIL Climate is produced by the MIT Environmental Solutions Initiative at the Massachusetts Institute of Technology. David Lishansky is our editor and producer. Aaron Krol is our scriptwriter and associate producer and did our artwork. Michelle Harris is our fact checker. Ilana Hirschfeld was our production assistant. Sylvia Scharf is our climate education specialist. The music is by Blue Dot Sessions, and I'm your host and producer, Laur Fisher. Thanks so much to Professor Desiree Plata for joining us again, and thank you for listening.